Okay, so I'm going to start on notes 6.2 dot product of vectors, but this is kind of one of those things that some of you like to do because it's like simple algebra skills. But another big concept here that I want you to realize or make sure you know is that when you have the dot product of as multiplying two vectors together, when you multiply two vectors together, you actually get a scalar. You get a number, not another vector. Here are some properties that we're going to probably use today or within this section of multiplying our vectors together. One of the things, too, I want you to make sure you understand or see is that the different forms, if they're in component form and I'm multiplying vectors together, you're going to multiply this tells you I'm going to multiply my A components, or my first components together, and add them to, then multiply the second components together, add them together. Kind of proves to you how you're going to get a number, not a vector. Okay, so the first example one, it says to find that each dot product, you have a vector in a component form, and its component form is 3, 4, and this, you're going to multiply times another vector. It doesn't give you the name of it. It's in component form 5, 2. What I'm going to do is I'm going to multiply those together. To do that, I'm going to multiply your first components together, and then you're going to multiply the second components together. Or as operations tell you, you're going to have to multiply first. So I'm going to have 15 plus 8, and that's going to actually be 23. Not so hard. Not a hard concept on the multiplying vectors. Why the mess you're going to use this, you will find out later why you actually have to use dot product to find, you're going to find the length of a vector using dot product. Or you're going to apply this. It's just a skill. But in example B, I'm going to do the same thing. I'm going to multiply first components together and add them to my second product of my second components. Multiply together. Negative 4 times 1 is negative 4. Negative 2 times 3 is negative, oops. I should probably use an eraser. Minus 6. Lo and behold, you get negative 10. Kind of should tell you that when I'm multiplying these two vectors together, I'm going to get a negative number. Okay. Now, what's weird about the the last option, or the last example, or example C, is look at the form that I'm in. Guys, this isn't component form. This is in that linear form that we said you probably see in physics. But the same properties are going to hold true. I'm just going to kind of multiply my like components together with my like components. So what that's telling me is I'm going to multiply, see I have these 2i and 3i, I'm going to multiply those together. Run out of room. Okay, so I'm going to multiply 2 times 3, your I components. Okay, I really don't need that I here, but I'm going to multiply those together as my first components, and I'm going to add it to negative 1 times negative 5. Again, I'm running out of room. I'm erasing this. They give you notes to conserve space, but whatever. Again, when you multiply the dot product of two vectors, you get a number. 2 times 3 is 6, plus 5. My answer's going to be 11. Okay. Now, on this I don't know why you don't have example 2. I must have old notes. Okay, well, I'm going to go on. I'm not sure why you don't have an example in here. Let's see if we go to the next slide. Okay, angles between vectors. I guess let's talk about if you have vectors u and vector v are two non-zero vectors in their standard position. The angle between u and v, you can find that angle between those two vectors by that formula that's given, the angle between two vectors. You can use this equation. Big difference is, when is to find the angle? This is just a formula. To find the angle, I actually have to use the inverse cosine of it to find actually theta. So what they want us to do, they gave us, in example 2a, they've given us two vectors, in vector u and vector v. They're both in component form, and they want us to find the angle between them. Well, there's several different ways of doing this. Again, in that formula, if you notice, that they want us, you have to find the magnitude. You have the absolute value u and absolute value v. It's wanting the magnitude, so that's always where I'm going to start. The magnitude of u is going to be the square root of 2 squared plus 3 squared. It's going to be square root of 4 plus 9. Oh my god, it's the square root of 13. What is it with the square root of 13? Okay, well, anyway. So, that's the magnitude of u. I'm going to find the magnitude of v. Okay. It's going to be square root of 4 plus 25, which is our next favorite question. Problem is the square root of 19. Okay. What they want us to do, sorry about this. Now I gotta find out, put this in this equation. So if I want to find cosine of theta, it could be written as u times v over magnitude of u times the magnitude of v. Okay, well, lo and behold, guys, I'm gonna do dot product of these things. So I'm gonna multiply 2 times negative 2 plus 3 times 5 over magnitude of u is the square root of 13 times the square root of 29. Okay, this is going to be cosine of theta equals negative 4 plus 15 over the square root of 13 times the square root of 29. If I wanted to, this would be 11 over, I'm actually going to figure out what 13 times 29 is. Square root of 377. Multiplying radicals, you just multiply the numbers underneath. If I want to find theta, it would be the inverse cosine of this, 11 divided by 377. Square root of 377. So let's do that. Inverse cosine of 11 divided by square root. Okay. And theta, the angle between those two vectors happens to be 55.5 degrees. Okay, not so bad. Alright, I'm going to do example 2b. I'm going to slide over here. Oh, I really can't do that. Okay. I'm not sure what's on the next slide, but let me see if I can find some room. Oh, crap. Okay, example 3b. Okay. It gives me the vector I hope this is right. I'm given two different things. Hold on a second. Okay, sorry about that. They give it to you in example 3b. They give you this vector, instead of it in component form, they give it to you in this linear form, which is okay. Same rules apply, guys. Still want to find the magnitude of u. It's going to be the square root of 2 squared plus 1 squared, which is the square root of 4 plus 1, which is the square root of 5. Okay, the magnitude of v is the square root of negative 1 squared plus negative 3 squared, which is the square root of 1 plus 9, which is the square root of 10. Oh, well, it's something other than the square root of 13. How about that? Okay, the same formula, guys. This is just a different form. The rules apply. If it helps, A is going to be 2 in this problem, and B is 1. And for vector V, my A is -1, and B is -3. It's the same formula, just looks kind of different. Okay, but now I'm going to plug it in this equation. So cosine of theta can be written as U times V over the magnitude of U times the magnitude of V. Lo and behold, I'm going to be doing some vector multiplication. 2 times -1 plus 1 times -3 all over absolute magnitude of U, which is the square root of 5, times the magnitude of V, which is the square root of 10. It's funny that it does that. Sorry. Okay, so I have where am I going with this, guys? This could reduce. This reduces to -1 over the square root of 2. Okay, so I want to find the cosine of what angle gives me -1 over the square root of 2. I imagine you pre-AP kids could probably do this in your sleep. The cosine of one angle gives me -1 over the square root of 2, or if you rationalize it this. Theta, without a calculator, is going to be 135 degrees. Because it's in that, I'm multiplying those two together, and it's going to be the angle between them. If you want to have this in the calculator, if I want to put this in your calculator, you can do it this way. Inverse cosine of -1 divided by square root of 2 would be 135 degrees. Okay. I'm pretty much going to stop right there. Okay. One of the big things here that we're going to do is show that if the angle, two vectors are perpendicular, if their dot product is 0. And really what that means is if you have vector U times vector V, if we did that using like same thought, the magnitude of U times the magnitude of V times cosine of 90 degrees, cosine of 90, it's going to be 0. And that's because if I remember that the cosine of 90 happens to be 0. So 0 times the magnitude of U and V, that's going to be 0. So that means that vector V and vector U are orthogonal, which is another word for perpendicular, if and only if their dot product equals 0. Therefore, that these two vectors are perpendicular or orthogonal. Okay, so let's do an example of this. What they want us to do is prove that vector U and vector V are orthogonal. So they really want us to show, this is an example. That vector V in component form, vector U in component form is 2, 3. And vector V in component form is -6, 4. I need to prove that they're orthogonal. So what I'm going to do is find the dot product between these two. Okay, so I'm going to multiply 2 and -6 plus this is a positive 4. No wonder I was doing that wrong. Plus 3 times 4, and that's going to be negative 12 plus 12 equals 0. And since the dot product is, when I multiply the two vectors, their product is 0, that means that they're perpendicular. Okay.